All right. Welcome to the Week 10 review for Math 2417. This week we'll be going over inverse functions, exponential functions, some bases other than e, and some indeterminate forms of limits and L'Hopital's rule. All right, so I guess we'll start just with some basic inverse functions. We did talk about this some last week, so we'll just go ahead and recall that a function probably has an inverse if it passes the horizontal line test. So if we have a function like, let's say this, it needs to pass the horizontal line test. For instance, here we can draw a horizontal line. It'll intersect our function at more than one point. So this does not have an inverse. And in order for a function to have a true inverse, it has to pass this horizontal line test. Okay, so let's go ahead and talk about how you actually go about finding an inverse of a function. Okay, the first step is always make sure that your function passes the horizontal line test. The second step is to swap x and y in your function. And then lastly, you need to solve for y. Let's go ahead and do an example just to illustrate these three steps. Let's say that f of x is a function, so function y equals to square root of 3x plus 1 and then minus 2. So in this case, we would need to make sure that our function passes the horizontal line test. Since it's a square root, it's going to look something similar to this, which clearly passes the horizontal line test. Our next step is to swap x and y in our function. So instead of writing y equals to the square root of 3x plus 1 minus 2, we would write x equals to the square root of 3y plus 1 minus 2. Our final step is to solve for y. So we need to first add 2 over. Then we square both sides. And we subtract 1 from both sides. That should be x. Minus 1 is equal to 3y. And lastly, we divide by 3, and we get y equals to x plus 2 squared minus 1 divided by 3. That is our inverse function. However, we need to actually make one other adjustment. That is, we need to specify the domain of this function. Because if we just graphed this, we would get our full quadratic. It would look something similar to this. It might be a bit wider, but you'll notice this function actually doesn't pass the horizontal line test. What we need to do is we need to consider the range of this original function, which is from -2 to infinity, if you recall, because the range of the square root of x is anything bigger than or equal to 0, but then we shift it down 2, so then it's anything bigger than or equal to -2. That's our range. And the domain of our inverse function is the range of our original. So we need to specify that x is bigger than or equal to -2. that will actually get us just this right-hand half of our function. So this is our inverse. And it would look something like that. Make sense? Cool, cool. So I guess we'll go ahead and do a couple of brief practice problems. Your job is to find inverses and the domains of the inverses. So your first problem is going to be x squared plus 2x plus 4 for x is bigger than or equal to -1. And this function is only defined for x is bigger than or equal to -1. Just a quick statement. And then our second question is going to be y equals to 4e to the 3x minus 1. Let's go ahead and give those a try. Just give me a heads up when you finish. All right, how's it coming? Stuck on the algebra for 1. All right. It is a bit difficult unless you do something specific first. Let's actually go ahead and talk about what we should do on problem 1. Are you familiar with completing the square? Sort of? Okay. Let's just do a brief review. Actually, in this case, I'll go ahead and do a brief review of completing the square. When you complete the square, we want to look at specifically the second term, and we say, okay, I'm going to take half of that 2. In this case, half of 2 is 1. So we would write x plus 1 squared, and then we would instantly subtract 1. Because if we expanded x plus 1 squared, we would get x squared plus x, multiplying x by 1, plus x again, and plus 1, which is x squared plus 2x plus 1. But then if we subtract 1 afterwards, that's just x squared plus 2x, which is exactly these first two terms. So if we complete the square on this problem, we would actually end up with x squared, sorry, not x squared, x plus 1 squared minus 1, and then plus our 4 at the end. So we get x plus 1 squared plus 3. And if you're looking for the range of this, which we'll need to find the domain of our inverse, it's just everything bigger than 3. Does that make sense? Cool. Completing the square is pretty helpful for finding inverses of quadratics, because then it makes your algebra later on a whole lot easier. Of course, we can also see that our vertex of this quadratic is at the point -1, 3. So since x is bigger than or equal to -1, we're just going to have half of our quadratic, and we can see that it's 1 to 1, so it'll have an inverse as well. If we wanted to sketch out a brief little picture of that, we'd have our point -1, 3, and our quadratic would be going upwards like this, just on that 1/2. So we know that it's 1 to 1, so it has an inverse. Our next step is to swap x and y. So since y equals to this, we would have x equals to y plus 1 squared plus 3. So x minus 3 equals to y plus 1 squared. So y plus 1 equals to the square root of x minus 3. So y equals to the square root of x minus 3 minus 1 is our inverse, provided we have the domain of 3, infinity, because we need to take the range of our original function. And that is our answer. Does that make sense? Cool. Did you manage to take a look at number 2? All right. Why don't you go ahead and try to find the inverse of that one really quickly? Actually, have you talked about finding the inverse of exponentials at all? No? Okay, in that case, let's just do this one as an example. Because it is a bit awkward if you're not used to it. First off, you need to find the range of this function, y equals to 4e to the 3x minus 1. Well, we know that 4e to the 3x is always going to be bigger than 0. So 4e to the 3x minus 1 is always going to be bigger than -1. So our range is -1, infinity. You'll notice we're not using a bracket. we're using curved parenthesis because for e to the 3x will never be equal to 0. That's one of our properties of exponentials. And if we were to sketch this out, you can recall the basic shape of an exponential graph. It's kind of like this. In this case, I'm shifting it down 1, but it's clearly 1 to 1, and it passes the horizontal line test. So it should have an inverse. Now our next step is going to be to switch x and y. So we have x equals to 4e to the 3y minus 1. And now we need to solve for y. We always want to move in reverse order of operations, which means we need to get rid of our addition and subtraction first. So x plus 1, if we add 1 to each side, equals 4e to 3y. Next is multiplication. So we get x plus 1 all over 4 equals to e to 3y. And now we can look at exponents. Do either of you remember how to cancel out an e? Right, we take the natural log of each side. So we have the natural log of x plus 1 over 4 equals to the natural log of e to the 3y, which is just 3y. And lastly, we just need to divide both sides by 3. I suppose that would be there. We get y equals to 1/3 natural log of x plus 1 over 4 as our inverse. And of course, its domain will be everything bigger than -1, not including -1, because that was the range of our original function. That makes sense? Cool. Okay. I think that's enough of inverse functions for now. So we'll talk about exponential functions. Let's see. Exponential functions. Okay, so in general, our just very basic exponential function is y equals to e to the x. And it is defined to be the inverse of the natural log of x. So what this means is e to the natural log of x is equal to x because they cancel each other out. And also the natural log of e to the x is equal to just x, because these two functions are inverses. And this is an important property because it's how you manage to take the inverses of functions involving natural log or e. And it's just very helpful for algebraic simplification. So let's talk about some properties of our exponentials. And I guess we can say, and we'll talk about bases other than the next one. So some properties. Our function e to the x is constantly increasing, also known as monotonic. And because it is monotonic, it has a true inverse, and that is, again, the natural log of e to the x. Additionally, its range is all numbers that are bigger than 0, and its domain is all real numbers. And of course, that means that the range of natural log is all real numbers, and the domain of natural log is everything bigger than or equal to 0, because they're inverses. The domain of natural log is the range of e to the x, and the range of natural log is the domain of e to the x. Next, we'll talk about the limits as x goes to positive and negative infinity. The limit as x goes to negative infinity of e to the x is simply 0. And the limit as x goes to positive infinity of e to the x is equal to positive infinity. A couple of important values of e to the x. E to the 0 is equal to positive 1. If you have two numbers, a and b, or even two functions, a and b, and multiplying e to the a with e to the b, that is the same thing as a e to the a plus b. This is one of your exponent rules. And lastly, we'll talk about the integral and derivative of e to the x. So the derivative with respect to x of e to the u is e to the u times du. So if we had e to the 2x, we wanted to take the derivative, it would be e to the 2x times the derivative of 2x times 2. And lastly, the integral of e to the u times du is simply e to the u. So those are all some important properties of exponential functions. And I've got some practice problems, and they're basically just designed to get you more familiar with working with e to exponentials. And I think I put in a couple of natural log problems as well. Alright, here goes. I'll go to this top one. Okay, so for some practice problems, let's say we want to define the integral of 5x e to minus x squared dx. Okay, go ahead and give these three problems a try. And if you get stuck on one, don't worry about it, just see if you can solve the others. For a, that's e to the negative 2x. Let's see. Careful. Do you mean to put e to the negative x squared? Go ahead and go over a really quick. Yeah, I figured. Let's see. I'm going to want to use u substitution to let u be the more complicated part. In this case, we have an e to the negative x squared. So we're going to let u equal to negative x squared. So then du is negative 2x dx, or in other words, negative x dx is equal to, or let's go with positive x dx, is equal to negative 1/2 du. So we can rewrite this as 5 over 2 integral e to the u du, which is negative 5/2 e to the u plus c. So our answer is negative 5/2 e to the negative x squared plus c. Nice work. And that box just went right through. There we go. All right, nice work. Have you worked on the other ones at all yet? All right, did you get B yet? Go ahead and make your answer out if you got it. Yes, what method should we use in order to integrate B? The natural log of 1 plus e minus the natural log of 1 plus e 0. All right, let's go ahead and double check that. Here we go. So in this case, again, we want to use u substitution and let u equal to the more complicated part of our equation. In that case, that would be the 1 plus e to the x. And du would just be e to the x dx. So our integral simplifies down to integral from, well, I guess we would have du divided by u. Let's go ahead and change our limits actually. If we plug 0 into u, we would get 1 plus e to the 0th, which is 1 plus 1, which is 2. So we would have going from 2, and our top limit would be 1 plus e to the first, which is just 1 plus e. And the integral of du over u is just the natural log of u. Then our limits are now 2 to 1 plus e. And we just plug in the top limit, natural log of 1 plus e, and subtract the bottom limit, natural log of 2. So you're exactly right. Just remember e to the 0th is equal to positive 1. Nice job. Have either of you worked on number 3 at all? Or part C, I guess. Yeah? Did you get it? Let's just go over it. So if you recall, in order to write the equation of a tangent line, you got y minus 3e squared plus 1 equals to 6e squared times x minus 1. All right, let's check that. So if you recall, in order to write a tangent line, we need a point, x1, y1, and a slope in. And in order to, our equation of a line would look like y minus y sub 1 equals m times x minus x sub 1. And in this case, we already have a point, 1 being our x1 and 3 squared plus 1 being our y sub 1. In order to find our slope, well, slope is just the derivative. So we take the derivative of our function. That's going to be 3e to the x squared, 3e to the 2x, multiplied by the derivative of 2x, which is 2. That's 6e to the 2x. And then we need to plug in our x value. So f prime of 1 is 6e squared, and that is our slope. So then we just plug everything into our slope equation of a line right here. So y minus 3e squared plus 1 equals to 6e squared times x minus 1. And it is important that you have these parentheses right here and right here, because that, if we wanted to drop those parentheses, we would actually get y minus 3e squared minus 1 equals to 6e squared times x minus 1. That is our final answer. Make sense? Cool, cool. All right. Let's go ahead and move on to talking about some bases other than e with regards to exponential and logarithm functions. So we talked a lot about functions that look like e to the x and functions that look like the natural log of x. The natural log of x is actually log base e of x. What if we wanted to talk about functions that have a base other than e? So instead of having e, we had, say, 2 to the x, or log base 2 of x. Derivatives and integrals aren't actually quite the same, but they're very similar. Let's say we had just a generic a to the x, where a is some constant, other than 1. Because if we had 1 to the x, well, that would just be 1 no matter what number we put in it. So if we wanted to take the derivative of this, we could actually say y is equal to a dx. So then we're going to use a method called log differentiation. And what happens is we take the natural log of both sides. Because that allows us to actually bring our x down out front as a coefficient by one of our log rules. So now if we took the derivative of both sides, I'm going to put this up here, we get that 1 over y times y prime is equal to the natural log of a. Because natural log of a is just a constant, we take the derivative of x times the natural log of a, we get just the natural log of a. So y prime is y times the natural log of a, but then y is equal to a to the x. So y prime is natural log of a times a to the x. And that's how you take a derivative of something other than of an exponential that has a base other than e. In general, you don't have to go through this whole log differentiation process. The derivative of natural log of a, not quite. Remember, since a is just a number, natural log of a is just a constant. In fact, we could call it like c or something. So then the derivative of cx, because we had right here an x right there, so the derivative of a constant times x is just a constant. Yeah, good question though. So in general, if we have some, generic exponential function with a base at some constant and an exponential of some function of x, the derivative is just going to be the natural log of your base times your original exponential multiplied by the derivative of your exponent. And if we wanted to integrate actually we'll talk about integrals in a bit after we talk about how we would take the derivative of the generic of a generic logarithm that has a base other than, so a log that's not a natural log. In this case, something you may not know is that log a of sum of x is 1 divided by the natural log of the base times the natural log of what's inside. And this is actually, again, pretty easy to differentiate because the natural log of a is a constant, so we have the same constant times a function situation we had earlier. So y prime is we leave our constant alone and multiply by the derivative of the natural log of x, which is 1 over x. And if we simplify, that would be 1 over x times the natural log of a. And of course, if we wanted to generalize this and put it in terms of u, where y is equal to the log base a of u, then y prime would just be 1 over the natural log of a times 1 over u times du. So easy enough. That all makes sense? Cool. All right. We'll talk about just a couple of practice problems that don't involve calculus. So what is x if 2 to the x is equal to 164? And what is x if log base 5 of x is equal to, here, let's see, if log base 5 of x is equal to 4. Pain. Aw, come on, these aren't that bad. Fun. You have an interesting definition of fun. what power will make 5 equal to 4? Yeah, that's not quite the way you want to think about it. In this case, logarithms are like anti-exponentials. So one way to think about it is 5 to the 4th is equal to x, because like undoing it. I guess one thing to think about is, if you recall that, so if we wanted to undo natural log, we would raise both sides to the power of e, right? Because e to the natural log of x is just x. In this case, since our base is 5, in order to cancel out that natural log, in order to cancel out that log base 5, we would raise both sides to do 5 to the power of each side. And we make the 5 and log base 5 would cancel out, so we're left with x equals 5 to the 4th. 5 to the 4th is 625. 25, I said 625. Yeah, neat stuff, huh? All right, did you get part A? 6. Not quite. One way to think about it is to, let's see, we know that in order to have a fraction, x should be negative, right? So we could also rewrite this as, I guess if we, what's the best way to put it? You said -6. Okay, there we go. -6 is correct because 2 to the -6 is equal to 1 over 2 to the +6, and 2 to the +6 is 2, 4, 8, 16, 32, 64, so that would be 1 over 64. And again, you could actually cancel this 2 to the 8 by taking the log base 2 of each side. But if you're not familiar with how to do logarithms, this isn't a huge help, not as much of a help as in this case when we were able to do 5 to the 4th is equal to x. But yes, you're exactly right, x is equal to -6. All right, so now I guess we should probably talk about doing some actual differentiation and integrals. We'll start with just a couple of derivatives though. So go ahead and take the derivative. Equals 2x plus 2 times log base 7 of 4x squared minus 1. Cool. Yeah, we'll start with just those two. And if you recall, just go ahead and try those out. And if you would like me to put up the differentiation rules for log and exponents again, I can do that. Yes, please. All right, give me a sec. So if you recall, That's for the derivative of a logarithm. And for an exponent, actually we'll make that in terms of u. There you go. You're welcome. All right, did you get it? 2 to the 3x plus 2 times 3 times the natural log of 2. Perfect. Remember, we can just use our standard rule. Derivative of, in this case, 3x plus 2 is our u portion. We would have our base is u. So our first derivative is the natural log of our base 2 times our original function times the derivative of the exponent. So you're exactly right. What about for b? Actually, b is probably going to be a bit of a pain to type out. We'll just go ahead and write it out for you. In this case, our base of our logarithm is 7. So we have 1 divided by the natural log of the base multiplied by 1 over, yep, 1 over 4x squared minus 1 times the derivative of the inside of our logarithm there, times the derivative of 4x squared minus 1 is just 8x. And that would be our answer. There's not really a ton we could do to simplify it. We could write it all as one term, but this is fine. Okay. And next I think we'll talk briefly about integrals of exponentials. So let's say you wanted to integrate a to the x dx. Well, in this case, we have to have 1 divided by the natural log of a times a dx plus c. And if you recall, that's because the derivative of a to the x is equal to the natural log of a times a to the x. So if we had just natural log of it, just a to the x, then we would need a 1 divided by natural log of a in order to cancel out that that natural log of a that comes along when we take the derivative. That's why we have 1 divided by the natural log of a there. And it's the same principle if we have just a to the u. We've got du. It would still be 1 divided by the natural log of a times a to the u plus c. So pretty straightforward. Go ahead and give you a couple of, actually, I'll do one quick example. integral of 4x times 3 to the 2x squared dx. In this case, we would want to let u equal to our exponent, 2x squared. So du is 4x dx. So this integral becomes exactly 3 to the u du. Then that is 1 divided by the natural log of our base times 3 to the u, which is 1 over natural log of 3 times 3 to the 2x squared. All right, and now I think a couple of practice problems would be good. So there's one, and for writing the natural log of a, does it need to have an absolute value? It really depends. Because if you recall, we can't take the natural log of a negative number, but a lot of the times we know the exact value of a. So, for instance, in the previous example we had a was equal to 3. So the natural log of the absolute value of 3 is the same as just the natural log without the absolute value. No problem. Go ahead and try these 3 out. I'll give you a couple of brief minutes. You're stuck on C. All right. In that case, let's go ahead and just start working through the solutions, and then we'll get to C. So the integral of 2 dx dx, that's basically just our standard generic form. You can just go ahead and integrate that. 1 divided by our base times 2 dx plus c. That's our answer. That's just straight off our rule. For this one, we're going to need to let u equal to the natural log of 4 times x. So then du is the natural log of 4 1 divided by the natural log of 4 times du. So we end up with 1 over natural log of 4 times the integral of 8 to the du, which is 1 divided by the natural log of 4 times 1 over the natural log of 8, so times the natural log of 8, times 8 to the u plus c. So our answer is 1 over natural log of 4, natural log of 8, times 8 to the natural log of 4 times x plus c. Okay, now we're at part C. And this one is a lot easier than it looks, because if you recall, log base 2 is the inverse of 2 to the u. So because these are inverses, they cancel each other out. It's like saying the natural log of e to the 3. So this integral actually just becomes the integral of 3x. Why did I write e? That should be 3x dx. And of course, that's just a very simple, straightforward integral. We have x squared plus c. That makes sense? Yeah. So part B, what we needed to do is we just made a u substitution. That's not where u was the power of our function. So we let u equal to the natural log of 4 times x. But the natural log of 4 is just a constant, so we can treat it like a constant. So our derivative of u is just the natural log of 4 times dx. We only have a dx, so I isolated dx. Yeah, natural log of 4 is just a constant, so that's why we treat it just like 1. We can pull it out of our integral, and then it just gets multiplied by the natural log, by 1 over the natural log of 8 later on that we get from integrating our 8. Alright, but does all of that make sense? Over C for just 1 second, of course. And of course, the trick for C is just recognizing that the log base 2 and 2 to the 3x were inverses, so we could cancel and just get 3x. Alright, let's go ahead and move on, because I would like to cover, you're welcome, we do need to talk about L'Hopital's rule. And this rule involves limits. So I'll just briefly give a definition of L'Hopital's rule. Let's say you have a limit as x approaches some point c of two functions f of x over g of x, and you get one of your classic indeterminate forms. So if you have like 0 over 0, or positive or negative infinity over positive or negative infinity, well, then you can actually say that the limit as x goes to c of f of x over g of x is actually the same as the limit as x goes to c of the derivative of x over the derivative of g. And one thing to note, this is not the quotient rule. Okay, so let's go ahead and illustrate this with a couple of examples. So let's say you had the limit as x goes to 0 of e to the 2x minus 1 divided by x. Well, if we plug in x is equal to 0, then you would get 1 minus 1 over 0, which is 0 over 0. And this is one of our indeterminate forms. So L'Hopital's rule says that we can actually take the derivative of the top, which is 2e to the 2x, and the derivative of the bottom, which is 1, and say that that is actually the same, just like that. And we can actually just plug in 0 for x. We get 2e to the 0th over 1, which is 2. So this limit is 2. Make sense? Cool, cool. A couple of tiles. Let's see. So you have to have indeterminate form 0 over 0 or an infinity over an infinity, because if you have like infinity over 0, L'Hopital's rule does not apply. And that is important to remember, because you want to make sure you're only applying L'Hopital's rule in the right cases. Stop. I'll just go to a different part of the board. Okay. So here's some practice problems. Determine if L'Hopital's applies, and then if it does, find the limit. Okay. Go ahead and try those out. You can't say the original function is equal to 0 to right. Yeah, because technically it's like it's not equal to it because it's in the name indeterminate. It's not determined. So we can't say it's equal to something that's unknown, because that just doesn't really make sense in the context. But what we would do is we would say it's equal to, say, like the derivative of f of x over the derivative of g of x, and then we would be able to find a definite answer. All right, let's go ahead and go over these problems because we're almost out of time. In this case, part A, if we plugged in 0, we would get 0 over 0 because that's an indeterminate form. L'Hopital's rule does apply. So we can say that it's equal to the limit as x goes to 0 of the derivative of sine x, so cosine x, over the derivative of x, which is 1. Now when we plug in 0, cosine of 0 is 1 over 1, so our answer is 1. For part B, if we plugged in 0, we would get 1 divided by 0. That's not an indeterminate form. So L'Hopital's rule does not apply. All right. For our third one, if we plugged in 3, we would get 9 minus 9 is 0 over natural log of 3 minus 2, which is the natural log of 1, which is 0. That gives us 0 over 0, which is an indeterminate form. So L'Hopital's does apply. We can take the derivative. We would get 2x divided by 1 over x minus 2, which is 2x times x minus 2. And now if we plug in 3, we would get 6 times 1, so our answer is 6. And lastly, for E, if we plugged in a number close to negative infinity, we can see that this is approaching infinity over infinity. So that means that L'Hopital's does apply, and we can take the derivative. And that would give us 2x, the derivative of our top, and negative e to the negative x for the bottom. But then if we plug in something close to negative infinity again, we get that this approaches negative infinity over negative infinity. And this is another indeterminate form. We can go ahead and use L'Hopital's again. The derivative of 2x is just 2 over the derivative of negative e to the negative x is e to the negative x. And if we plug in a value approaching negative infinity, this is 0. So 0 is our answer. Make sense? Cool, cool.